Trying to finish up on chapter 21. Basically, the phenomena of inducing an EMF. So 21, induced EMF, we got Faraday's law, and then EMF in a moving conductor, all related, and I'll try to get her done. So we've got our review videos. I hope I'm remembering everything. I tried to read through the PDFs and make sure I was catching everything. You guys might use the comments to tell me what we missed and tell the class what we missed if you find something. So let's see what we've got. Let's get into the whiteboard because it's so awesome. Induced EMF. If you guys remember, this is the tricky one. It keeps coming back. That symbol. What does that symbol stand for, right? Well, EMF, yes. But it represents a potential difference. Okay, it's a potential difference. It's something that, if we remember, I mean, it's way back from chapter 17. If we've got a potential difference, anyway from 0 volts to a positive or to a negative volts, any potential difference, we can drive charge. We can drive positive charges one way, right? High potential, low potential. Or we can drive negative charges from low potential to high potential, okay? Anytime we have a potential difference. So the fact that we can induce an EMF, again, if we can remember that initial video, right, where what he had was a solenoid, right, a solenoid, and then this science teacher had a magnet, right, and he put that magnet into that loop. Now that loop was just connected to an ammeter, and it was giving us readings, right? This ammeter was giving us, it was microamps, but it was giving us readings of amperage. And it wasn't connected to anything special. There's no power source. There's no battery. But if I have a current, it means I've got a potential difference that's driving charge through these loops, which is pretty cool because we're essentially creating an EMF out of what? Out of a magnet and a coil of wire. Okay, it's fascinating. Say, the things that he did is he put one pole in, things that impacted that little meter, right? Things that impacted the meter was the rate of moving magnet, right? But also the pole, right? So the faster you enter the magnet into the loop, the higher the amperage. And then when they removed it and went the opposite direction, right? This way, that way. When he turned the pole, it had the opposite reaction. So the poles mattered, rate of moving magnet, rate of moving, and maybe direction of movement. Right? Of the magnet. Okay, those are all three things that created an EMF. Now that was 21.1, just the phenomena itself. And then we get into 21.2, right? Which was what? Okay, let me pause it. Faraday's law of induction and Lenz's law. Let me get those up there. All right, Faraday's law of induction and Lenz's law. Let's get the old whiteboard up. Faraday's law, right, wraps in what we are experiencing in the phenomena. When we move the magnet closer, you have a weak magnetic field to a stronger magnetic field. So there's this changing magnetic field. But Faraday's law helps us define another item, right, which is called flux. Little b says magnetic flux. And that is your field and the area which contains that field. I don't know if you remember that. Now, there's a little bit of extra here. I'm going to try to draw it. It's really hard. Okay, so, wow, my green. I'm just drawing those randomly. They're hitting through that field. I don't know if that portrays it much. Green really sucks on this. I'm just throwing the pen away. Okay, so the field, the amount of area that contains the field pertains to our magnetic flux. It's not our field per area, it's field multiplied by area. Now what they say is if I did an item perpendicular, right, if we remember geometry, if it's perpendicular to 2 dimensions of a plane, it's perpendicular to the plane, right? When my field is perpendicular basically to the, or when my area is perpendicular to the field, it gets the most field, right? So there's this angle, and basically it's cosine theta, because when these are lined up, right, the thing that's perpendicular to the surface and the field lines, they're lined up, that's maximized. So cosine of 1 or cosine of 0 is 1. So there's that cosine factor. So if I ever have that area tilted, that will change my flux. So different ways we can change our flux is impacted by the tilt of the area. So let's get into Faraday's law, right? Faraday's law says an EMF is produced. Now they have this negative N delta phi over delta T, okay? So the change in flux, or the rate and change of flux, right? So we can change our flux by changing how much field there is, maybe changing current, like there's a current carrying conductor next to it and increases or decreases in current. Or we can change our area by expanding or contracting, or we can rotate the area. Maybe the loop of wire can rotate through it. And actually, we can change area. We can change angle, right? Change area. And then we can change, right, the strength of our field. And we've seen several examples, right, of how to change the area. We had the bar on the loop wire that rolled back and forth. We did that in class, actually. We can change our angle by rotating the loop. We can change our B by increasing current in a current carrying conductor. That changes the field around the conductor. And that was our example where we had, right, this current next to a loop, and which way was the EMF induced. Okay, so that's how we can change our flux, and the rate at which we change it is just a time interval. N is standing for the number of loops in the coil, right? So you can double the EMF if you do 2 loops, right? And then this right here is Lenz's law, okay? Lenz's law, a little trickier to talk about, so what I'm going to do is pause again, pull up Lenz's law, and then go through an example of Lenz's law, okay? All right, it's going to be totally choppy, but that's fine by me. Here is Lenz's law, okay? Lenz's law, current produced by an induced EMF, right, moves in a direction so that the magnetic field created by the current opposes the original change in flux. So if I have a change in flux, I'm inducing a current that opposes that change. It's like this yin and yang. Increase this, I got to decrease it. Okay. Now there is another way to say it. An induced EMF is always in the direction that opposes the original change in flux that it caused it. Okay. You choose your way. So let's go through an example, and then I'm going to be done with 21-2. Okay. So I've got a current carrying conductor, and I want to know which way its field is going. Right? So I use my right hand rule and I wrap around it. It looks like it's coming out, so I'd have dots on this side. And then I'd have X's on this side. So it's going in to the board, okay? So my field is into the board and it's decreasing, okay? So into the board, right? And it's decreasing, okay? So it starts out strong, and then it rolls back, okay? So forward to backwards. I want to oppose that change. So I'm going to roll from back to forward, and that's going to create a current like this, okay? what if we were increasing, right? Increasing. Field is still into the here, right? And it's increasing, goes back into the page. So I want to oppose that, right? I'd rotate, I oppose it, and that would send it the other direction, okay? So we had examples in the book, 2 examples in the book, and you've got an assignment for it. All were something that were challenging us, working our brains a little bit. It's not easy, it's all visualization, so I want you to try to do those, and I'm hoping someone's going to create a video to go through. I forget what number it was, okay? Let me pause and get 21.3, okay? Sorry, this video is a little long, but I wanted to work through this and get it all in 21.1 in one video. EMF in a moving conductor is basically, if we start here where we've got a wire kind of partial U, and then we've got a conductor moving across it, so it creates this loop right here, creates that loop. And if it moves, what is it essentially doing? Now there's some derivation down here to get to this equation. I want you to review that, but the EMF, right, is the field times length times the speed at which you move that bar. Okay, so the length of the bar, you saw that in the video, okay, that length, and the speed at which it moves. So we got to understand what those parts are. So let's go to the screen and kind of work through that, and then we'll go down into this guy right here, why it works without a loop. Okay. All right. So EMF equals the field strength, length, times V. Now, when I move this that way, right, what's happening, right? My field is changing because what am I doing to this field? I am increasing it to this new location. My field has increased, right? It has increased. So I'm going to get a current. So right now, my field is out, right, of the page and through that loop, and it is increasing, okay? So that means Lenz's law says the current is going to be induced to oppose that. So I went from back to forward, so I go here, back into it. So my direction of my current, I'm bringing the green back in, the direction of my current is that way, okay? So what have we done? We've taken conventional current all through this, right? And we've taken those positive charges and we've moved them this way. And all my positive charges are moving this way. Well, what's that mean? If I just had a bar, like an airplane wing, right? It's not necessarily changing a loop or anything as it moves with speed, but what it is going to do, they found an experience where it actually, again, drives that charge. So again, my field is this way, right? And then it's increasing. I want to oppose it. My charges, my positives, are going to get up here, and my negatives are going to end up down there, right? Or was that opposite? Right, I think that was opposite. I have my negatives up here and my positives here, okay, with the right-hand rule, and it's driving this polarity, which gives us that delta V, right, which is an EMF, okay? So take a little bit more. We'll look at that phenomena. That might be a video conference as we go through and clarify which direction goes where. Like, does positive really go down when I'm moving this way? We'll practice that right-hand rule. Okay, I hope you guys are well. I will end and load this video and talk to you later.